So our first speaker is Douglas Fontes, and his talk will be on lunar regolith particles interacting with a lander rocket plume at low altitude. Douglas, please take it away. You have 10 minutes.
Thank you, John. So this is the title of my research, my study. Thank you for the introduction. And this study was also made in collaboration with Philip Metzger and James Montavani. So why should we investigate rocket plume interacting with regolith? Essentially because of issues associated with damaging structures around and also crater formation. Numerical modeling can provide key information about the velocity and angle of the ejector that can be used to design effective ways to reduce potential damage caused by the descending of the lander on lunar surface. In comparison with previous lander sizes, larger landers intended for human landing exploration on the moon, we will have higher momentum of the rocket plumes as well. That's going to directly influence how the dynamic forces act on particulate, which also affects the erosion mechanisms. The higher energetic flow increases the potential for damaging nearby structures and the lander itself during its descent. The main goal of this study was to investigate numerically particle trajectories under the influence of a 40-ton lander at different altitudes. The particle diameters ranged from 1 micrometer to 1 centimeter. And the initial radial position of a particle ranged from 1 to 10 meters from the center line of the rocket jet. To obtain some insights of the realistic interactions between rocket plumes and particulates on lunar environment, we simplify the problem to a physical model defined by some hypotheses, boundary and initial conditions, as well defined fluid, environmental, and particulate properties. This simplified model is then represented by appropriate transport equations and correlations that can be solved using a numerical model. The numerical solutions returns information that can be used to better understand the interactions and properly act on technological issues to reduce the risk of damage due to the ejector. So in this slide, we have the velocity magnitude, density, pressure, and temperature fields of the rocket plume. These figures are longitudinal plane in the mid angle of the quarter domain, where red color represents high values and blue color represents low values of the shown variables. In the top left corner, we have the velocity magnitude of the rocket plume at different altitudes of the lander. So we can see that there is a shock waves in a bowl format beneath the nozzle exit for all altitudes except for a lander at 1 meter. In the top right corner, given the logarithmic scale, we can observe how a fast density as well pressure reduces with radial distance from the center line of the rocket jet. These reductions in the gas density and pressure limit the drag force effect on the particles to a certain distance that does not exceed the numerical domain. The rocket plume temperature indicates the local level of agitation of molecules that influences how they transfer momentum to a particle. As we can see in the boundary layer and in the shock wave, the molecules are more energetic, which allows more momentum transferring from the flow to the particles of the regolith. Due to the drag force, regolith particles will be ejected from their initial positions, reaching high velocities according to the crossed plume flow region. When particles leave the numerical domain, the drag force is negligible because of the fast plume expansion, and those particles will follow basically ballistic trajectories only. Pressure and shear on the bottom surface are important measures to quantify possible erosion and particle lifting mechanisms. In these plots, we have top views of the bottom surface of the numerical domain, where each quadrant corresponds to a different lander altitude. The levels of shear stress and pressure varies with altitude. The lower is the lander altitude, the higher the pressure and shear are. As we can see, the pressure is maximum at the corner of the domain, while the maximum shear stress occurs at a certain radius from the center line of the rocket jet. This is due to a combined effect of the density and the velocity in the boundary layer for the shear stress. These figures show particle trajectories plotted on a longitudinal plane X and Y. X represents radial distance from the center line, and Y is the vertical distance from the bottom surface to the rocket exit. In the left side, we have particle trajectories for a lander at 1 meter in altitude, and in the right side, particle trajectories for a lander at 7 meters in altitude. Different colors represent particles initiated at different initial radial positions. Particle trajectories change in this animation for different particle diameters from 1 micrometer to 1 centimeter. Particle trajectories present lower angles when the lander is at 7 meters in altitude compared to the angles when the lander is at 1 meter in altitude. Also, larger particles are more likely to bounce than smaller particles, even inside the numerical domain. Just a reminder, the numerical domain in this case is 20 meters radially. In these figures, we plot the velocity magnitude of particles leaving this numerical domain. Each curve represents the variations of velocity magnitude with particle diameter for a specific initial position of the particle in the domain. In the left side, we have particle velocity curves for a lander at 1 meter in altitude, and in the right side, we have the same plot for a lander at 7 meters. The velocity of a particle leaving the numerical domain depends on its size, initial radial position, as well as the lander altitude. Particle velocities are higher when the lander is at lower altitudes. The maximum particle velocity predicted in this study was around 750 meters per second, when the lander was at 1 meter in altitude and particle size was 1 micrometer. The maximum velocity found in this work is below the lunar escape velocity. However, ground surface, including gradients, may affect the plume flow, leading particles to high velocity regions of the plume. Particles that go to those regions would reach higher speeds than the lunar escape velocity with greater damage potential. So final remarks, basically, this work provided information about angle and the velocity of the eject that can be used to estimate potential damage to nearby structures and develop strategies to mitigate damage caused by the ejecting. Particle velocities highly depend on the characteristics of the lander size, altitude, and the regolith size and position. The maximum velocity in this case was below the lunar escape velocity, but we need to remember that different soil topology and also mechanisms of rolling and bouncing may take particles to other plume regions with higher velocities. And a Randy correlation for particle velocity was developed is on a paper submitted to the Astronautical Journal. Thank you for your attention. I'll be glad to take any questions.
Great, thank you, Douglas. Does anybody have any questions? There's one in the chat. Do you use a CFD and or DSMC code to compute the gas flow? Sorry if I missed this, but also could you say a bit more about the boundary conditions that you assume at the lunar surface?
Yes, I removed some slides because of the time, but yes, I used the DSMC code to solve the rocket plume flow. And in terms of the boundary conditions, we had like wall surface on the bottom surface and symmetry planes for the quarter domain of this 3D numerical domain. And to represent this near vacuum condition, we had a high speed velocity in the outlet flow of the radial outer surface of the numerical domain.
Great, thank you. And there's one question in our time remaining from Michelle Monk. Was the surface always assumed flat regardless of altitude? Yeah, that's one thing that we need to explore. But in fact, we assumed that the surface is flat in all conditions.
but that's not it's not true for the real case. So we want to understand to model this using maybe dynamic mesh with the DSMC code to be able to simultaneously have the gas flow producing some crater during the descent. But we are working on this yet.
Great, thank you.